Right, good morning, everybody. I hope you are all well. Welcome yet again to another Wednesday webinar. I hope you're all keeping cool. That's going to sound very odd if you're watching this webinar in the middle of winter, but at the moment it means something to the people on the call. Fantastic again to be speaking to you guys about some practical case studies. And we've got Richard Bowman with us to do a kind of a revised edition of the RIBA 2030 case studies presentation he did a good few months ago for us now, given that Letty and RIBA have changed their carbon alignment targets. I know Richard's made some tweaks to some of his projects, and he can talk through those with you. But before we get into that, just by way of a bit of admin, as usual, if you guys can keep your mics on mute, and everybody will get the most that they can do from the presentation. Chat or questions, we'll answer them at the end, but use the chat box as usual to ask questions, and we'll try and get through as many as possible at the end to make it easy. And that's pretty much about it for the admin. That you've been on plenty of these, so you'll know what that's about. Next slide, Rich. Oh, we are recording the webinar, by the way. You guys will be more used to this now. This is all access to these videos or webinars through the kind of the MESHWORK platform, which is free. As I've said before, we're building tons of great content into this, and as of September, we'll be doing almost a kind of a topic-based month for our webinars for the coming year, and we are busily working away on our new embodied calculator, which we will be exclusively launching through the platform as well. So do tell all your friends, stick on there, start some conversation, share with us your sustainable projects, and let's get the conversation going. Next slide, Rich. And a quick 20 or 30 seconds just on Mesh Energy. If you're new to these webinars, we're an independent and holistic energy consultancy. We're based in Farnham in Surrey in the south of the UK, but do projects across UK and Europe and even further than that. And the primary reason for us being here is to partner with and collaborate with design teams to try and make sustainable design as intelligent and as easy as possible for you guys, so that you can really deliver fantastic, low energy, holistic, sustainable buildings to your end clients as well. And as you'll be well aware, trying to share with you guys what we know about what's changing, again, to just kind of try and keep you ahead of the pack as well. So without further ado, that's enough chatting from me. We're going to hand you over to Richard, and he's going to, as I say, give you an update on some of the RIBA 2030 projects that he's been doing. You're on mute, Rich.
Right. Morning all. Just a quick review.
Sorry, Richard, your mic isn't working there.
Really? Can you hear me?
Nope.
Okay, hang on a second.
I can hear him.
I was able to hear him, Doug.
Oh, right, okay. Somebody's saying they can hear Richard.
Yeah, I think everyone can.
Oh, right, I think you were good to go. For some reason I can't hear you, but everybody else can. Go for it.
That any better?
Perfect.
Go on, Richard, if you try speaking, let's see what happens.
Can you hear me now?
Right, okay, everybody else can hear you. I can't, Richard, but everybody else can. Keep going.
Okay. Right, so as we all know, the climate emergency has generally been declared by academic institutions, local governments, and professional institutions such as the RIBA, CIBSE, RICS, and so on and so forth. And so what we're all trying to do now, hopefully, is aim for carbon neutrality by 2050. And so we're sort of pursuing that net zero carbon goal. And what RIBA are trying to do is get us to focus on sort of the operational energy, and that's everything from computers to lighting to heating systems. It's the all-encompassing consumption of energy by a building. And we're also looking at embodied carbon, as well as now whole life carbon. And embodied carbon is really the manufacture, assembly of materials on site to create a building. So it's everything from cutting it down, digging it out of the ground, putting it through a factory, through to transportation and so on and so forth. And we're trying to ensure that the buildings are comfortable for our occupants and that we're driving down potable water use. And potable water use is drinking water. I mean, the same water you drink out the tap, we flush down our toilets, we do our washing with, and so on and so forth. So today, what I'm going to do is a short review and then cover what we need to know, what we need to do, things we need to consider, and then I'm going to go through 4 different case studies. And the latest one is particularly important, but we'll get to that. So, 6 months ago, Rebus targets were not building typology specific. And what's happened since then is that RIBA have done a little bit of work with LETI, the London Energy Transformation Initiative, and included some more building typologies such as schools. And so we're starting to build more and more numbers around what we're aiming for. And so regulated and we're looking at regulated and unregulated operational energy use, and we usually assess that using CIBSE TM54. And to give you an additional idea of unregulated use, it includes lift usage or escalators, and everything that doesn't really get captured by a Part L calculation. Embodied carbon, we said, is the creation, transport, and assembly of materials on site. But if you're working on projects in London, then we have to now report the whole life carbon. And this is really because the construction phase mainly constitute about 5% of the overall building life cycle. And I've saved an example of that right for the very end. Possible water we measure by completing building regulations Part G calculations. And for overheating, we use CIBSE TM59 methodology for domestic properties, and then TM52 for non-domestic. Just to put that in context, it's currently 27 degrees, so we're 1 degree below the limit of adaptive thermal comfort when it comes to overheating. So if it goes up another degree, we go past a line in the sand, as it were, where we can't sufficiently change our clothing or drink enough water or take any other physical, make any other physical changes that will enable us to not overheat. So let's put that into context for today. And then we look at daylighting, which is intrinsically related to overheating. You can have lots of glazing with plenty of daylight, but of course, put it in the wrong place and there's too much of it, then we're going to cause a passive thermal gain. And so we run the risk of overheating. And then indoor air quality is really looking at the relative humidity in the space, the CO2 parts per million. And there are specific studies around CO2 parts per million. So we know, for example, that if CO2 in a space goes above 1500, then you start to feel drowsy. So if you start to feel drowsy, you know that your air quality is not too good in your house or your office or wherever you might be. And also CO2 levels are a good indicator of the level of VOCs from materials that are in the space. And VOCs are volatile organic compounds, and that's things like formaldehyde that's used in glues to make MDF or chipboard, or it might be in paints, carpet, and so on and so forth. So what's changed? Well, The change is subtle, and it primarily lies with embodied carbon. But the trajectory for operational energy reduction has not changed with regard to the 2050 targets in mind. But the new building regulations slated for publication later this year expected to require a 30% reduction in operational emissions. So that's going to be interesting when it arrives. The occupant comfort criteria in the sustainable outcomes haven't changed. But the embodied carbon targets are generally increased by up to 50%. So what you can see on the graph at the moment is the domestic and non-domestic metrics. And the grey dotted line was the embodied carbon trajectory for the 2019 RIBA sustainable outcomes. And those have since been updated. And so that trajectory has moved. So we were kind of, with a lot of effort, we could have probably been in a really good place with our embodied carbon by 2035. But that embodied carbon has now become more lenient. And so the trajectory is now slightly shallower. And we're seeing that in both cases. And so the bar is, if you like, depending on your point of view, has been dropped. And we'll see why that's important as we work our way through the CPD. So the purpose of the climate challenge really is, it's all about whether it's limits, it's sort of bypassing limits and all targets and doing the best that we can. And so what we're looking for is step changes. And those step changes are in all across the industry, whether it's how we make our materials, what materials we use, the design process, and how we assemble them on site, the skills to assemble them on site, especially as new materials and technology appear as well. So there's all manner of changes that have to happen really over the next 10 years. We have to be very mindful of passive design of form and orientation. That has a big part to play on overheating. We also have to bear in mind the fabric first approach. So we're trying to make the fabric as efficient as possible before we start to apply energy systems. So what we're trying to do is reduce the amount of energy required to operate the building in the first place. Then we get into material specification. So that's the principles of construction and what the embodied carbon and whole life carbon will be as a result of that. And then we can apply renewable energy solutions, whether that be solar PV, solar thermal, air source heat pumps, or different methods of collecting heat through ground source heat pumps. And then finally, water fixtures and fittings. So if we're really going to, if we're moving into a heat and water stress period with climate change, then we have to ask ourselves, do we still need baths? If we, typically if we remove a bath from the Part G calculations, you can cut potable water usage in half. So there's great gains to be made, very simply, but there's a lot of behaviour change that has to go with this as well. And so what we're also doing as part of RIBA 2030, we're looking at unregulated loads. And like I said before, that's computers, that can be energy uses in kitchens, in offices, whether it's vending machines, occasional plug-in loads, there might be fans, there'll be lift usage. And then we've got overheating, which is either typically TM52 for non-domestic and TM59 for domestic. And then we've got a natural daylight. This is important because we know that the more natural daylight there is, then it's beneficial to occupant health and well-being, along with indoor air quality and CO2, which we measure through TM40. And then we can address VOCs and ventilation through approved document F. And what this means is we're able to provide evidence-based design-led projects. And you'll hear more about that when you're working in projects in London, for example, where the new London plan puts great emphasis on that. So these two graphs are for a campus that's currently in planning. So this was actually completed under the previous iteration of the Sustainable Outcomes Guide. But the operational energy side of the graph on the left hasn't changed too much. We've got the benchmarks there for the different RIBA years. We've got 6 different types of building there, ranging from a hotel to a restaurant, and then some sort of worker accommodation and so on. And then above that, the dots represent the current CIBC energy benchmark. So this was a good project overall to start with. What becomes interesting is you can see on the right-hand side is the embodied carbon graph. And although there was a high degree of refurbishment involved in this project, we were sort of edging up, we went above RIBA 2030 on the embodied carbon for the restaurant. However, where RIBA 2030 used to be around the 500 kilograms mark, it's now moved up to the new RIBA 2030 line. So because that bar has been raised, suddenly, this restaurant, which is highly glazed, is suddenly got an embodied carbon that will meet the RIBA 2030 targets. And these are the outcomes for the projects, like I said, it's currently in planning. So what does this mean in practice? Well, today we're looking at these typical U values to get through Part L. The thickness of the walls can really range from typically 300 mil up to about 400, depending on the materials that are being used. And what this means over time is, as we need to drive down operational energy by improving the fabric ever further, then the range of element thicknesses starts to increase. And the reason for this is essentially that low embodied carbon insulating materials have a reduced performance when it comes to thermal conductivity. So rather than having, for example, say 100 millimeters of PIR, if you're replacing that with wood fiber insulation, that may jump to 200. And so that continues to increase. And so potentially, if we want to go for a really high performing fabric with low embodied carbon, you could be looking at walls that are between 500 and 600 millimeters thick. And we've got that relative increase for the roof and the floor as well. And we're seeing this in pre-application drawings now as well. So how do we integrate this into a successful design process? Well, I mean, really, the 3 fundamental questions are why, where, and how in terms of the aspirations. The earlier those aspirations are defined in line with the RIBA digital plan of works, and then carried through the life cycle of the project, the more successful it will be. And the purpose of this really is to close the performance gap. And when I say performance gap, for those who may not already be familiar with it, if you do a Part L calculation, and the building is going to use, for example, 50 kilowatt hours per meter squared per year, is that when it comes to post-occupancy evaluation, you can see up to a 4-fold increase in actual energy performance. So that building may actually be consuming 200 kilowatt hours per meter squared per year. And so we're trying to set expectations in a more robust manner. It gives more certainty at pre-planning, so we're trying to eliminate design risk, and we can capture this very early on in the CIBC TM54 calculation, even before maybe doing dynamic thermal modelling, for example. We can do some very sort of desktop estimates, if you like, based on the internal floor of a building as to what that operational energy is likely to be. And there are tools for that. So what we're aiming to do is basically balance the 3 pillars of sustainability. Like I said, we're reducing design risk, but why this is of interest to the end user, if they're like a rental developer, for example, you may see a relative increase in capex, but also you'll see an increase in the rental value as well. And these sort of figures are coming from BRE. And so what you end up with a more efficient building is you should have reduced operational expense. You get the kudos for doing a highly sustainable building, a bit like Bloomberg in London. And also you're sort of taking that position on leadership in building performance and design and taking a sustainable path through. And so this is all embedded into the RIBA plan of works. Hopefully you're familiar with this. And so at stage 0, there's high emphasis on setting the aspirations. And then what happens in stage 2 is that those aspirations start to be turned into potential targets. And so you can see that there's a high degree of sustainable thinking very early on in the project. And then this carries on through to stage 2, where you're trying to realize it as conceptual design. And then gradually we're refining, once you've got the principles in place, we're then refining the design. And so we're getting a bit more number specific, as it were. And then we're really narrowing that down in stage 4. And then at stage 5, it really gets handed over to principal contractors to ensure that the aspirations and the design are carried out. And then we follow that up with a handover where you're sort of educating the occupants in how to use their building. I mean, we can design, a really efficient house, but unless it's used the way it's intended or to the best ability, it's not going to work out well in the long run. And so we can wrap that up in use through post-occupancy evaluation and do any nips and tucks as you go along to ensure that the entire life cycle of the building is as sustainable as it can be. So, first case study is an office. This is for Snug Architects. This is their office in Tottenham in Southampton. And they were looking to basically expand it and then create some second floor studio space. And so what they were looking for was achieving RIBA 2030 for the new upper floor. The ground floor is like the typical sort of brick block type construction with sort of a composite panel roof and what have you. And so looking at the operational energy for non-domestic buildings, you can see that the current benchmark has been dropped. And 2020 has now been dropped from the RIBA Sustainable Outcomes. We're at that point. We now need to start looking at 2025 and 2030. And as I said right back at the beginning, the end game for 2030 has not changed, but the target for 2025 has been lowered a little bit. So it's a little bit more ambitious than it was before. And I expect that this is to align with the new Part L that will be coming out. And so really the challenge was reconciling building performance with the capital cost. We found that we could reduce operational energy by 78% by replacing the heating systems and the lighting and so on and so forth, and improving the fabric. We found that we could pass the TM52 assessment on overheating, even though this large glazed area above the main entrance is largely glazed, but it didn't affect the overall performance. And we were able to use the dynamic thermal model to ensure that it didn't overheat. So how do we do that? Well, really we couldn't do too much to the fabric. So a lot of the operational energy reduction came from the solar PVs. But then we did look at, we put it into context by having a look at the building if it was an entirely new build. what we could potentially do with the performance of the building if we were looking at the element U values and making some significant improvements. And so where we could make incremental improvements, the big jump really was in the fact that taking that 2030 leap. And if you put that into context with a Part L calculation, so the as designed with the sort of minimum amount of PV, we still had a great improvement on Part L. So this is the dotted line at the top is the target emissions rate, and then this is what would happen if we improved the fabric and increased the PVs, and what happened to the Part L calculation if they kept the existing gas system. In comparison, if you add an air source heat pump, even not making many changes at all to the fabric, but adding PV, then we're also already looking at going negative on the Part L calculation. And then if we were to improve the fabric to 2030 level and maximize the amount of PV, then we're making some significant improvements. So we're changing the building emissions rate really from say 3.9 down to possibly 8.8 kilos of CO2, and that is a significant saving. And all this was done really through a whole number of iterations where we were looking at the as designed performance, so typical energy load, and taking into account typical energy loads compared with actual energy loads. I mean, these energy loads we derived from the electrical bills for the last couple of years to understand what the unregulated load was. And so we would be able to feed that into the model. And so then really did a whole number of comparisons. So whether we were improving the flat roof to new build, and what impact that would be. And so it enabled the client to make an informed decision really about what strategy to take. So what that meant was overall, with the refurbishment of the fabric, if the existing gas system was to be replaced and updated, then we could halve energy consumption to 80 kilowatt hours per year. But if we could switch that to an air source heat pump, then we're reducing the energy consumption threefold. And so we can get down new build operational energy right down to somewhere between 34 and 56 kilowatt hours per meter squared, which is very close to the 2030 targets for non-domestic properties. The next example is Hope Street, and this is a building being developed by a charity. Hopefully it's going to go on site this autumn. And it's a BREEAM outstanding project, hopefully. And we're looking as though we're going to get that. And it's been approved by planning. And when it comes to embodied carbon, what we did with this project was fundamentally, very early on at stage 2, look at the Green Guide to Specification, which is a database operated by BRE. And in there's a whole database of different types of building, types of construction associated with those buildings. And if you're wondering what to do about your principles of construction, but you're wondering how environmentally friendly are, then BRE put together examples of constructions in that database and give them their environmental rating. A bit like the EPC, I mean, basically A down to downwards, depending on how low the global warming potential is. And so basically what we did was we managed to target principles of construction where 2/3 of the would be A rated. The C rating is fundamentally the ground floor slab for durability. and then there's all the internal fixtures, fittings and finishes that's made up the remainder, and they were targeted to be grade B. So what this meant in real terms is you can see that the embodied carbon targets used today have been benchmark has been increased from 1,100 to 1,400 kilograms. But what was also interesting is, again, we're ignoring 2020 targets, but for 2025, that target has been increased to 970 kilograms of CO2 equivalent, and likewise 2030 has been increased as well. And I'll be able to demonstrate the significance of that in case study 4. So in terms of the principles of construction, we've targeted some very low U values, and basically it means we're doing a 60 to 90% reduction beyond Part L. And all this was developed using IESVE, so we've got a fully dynamic thermal model that simulates occupancy, plug-in loads, energy systems, PV, so on and so forth. And then this was exported into a tool called One-Click LCA, which is a global online platform where we can do embodied carbon and whole life carbon assessments of buildings depending on typology and location. And so what it meant was we could do some very quick comparative analysis on different types of construction. So we've got everything from concrete frames with sort of standard gas systems up to CLT with air source heat pumps. And actually, as a result, although the aspirations were there from quite early on, the final decision was to go for cross-laminated timber with air source heat pumps, and then there's some solar PV on the project as well, or quite a lot actually on the HMO, the building at the rear. And so what that meant was at stage 2, we had an embodied carbon of 196 kilos, but it's worth bearing in mind that this was only for the principles of construction. Once the energy strategy started to develop, then we've updated the figures, and so that does change. I should point out embodied carbon, there's the matter of sequestered carbon. And sequestered carbon is the carbon that's already been absorbed by the materials that are being used in the project, and therefore you cannot subtract sequestered carbon from embodied carbon to get a negative figure. That sequestered carbon figure only comes into play at stage D in a whole life carbon calculation, which is when you're looking at repurposing that material for other uses. So in this case, whether the CLT is being dismantled for and recut for a new project, or ground down for use in biomass, however it's going to be used, and that's so we ignore that. But we do have to declare it, and London Plan also requires that we declare that as well. And so overall, for a whole life, we were looking at about 1,000 tonnes of CO2 over 60 years, and a life cycle cost of about 9.7 million. And that life cycle cost is the operational cost of the energy, the water, maintenance, repair, replacement of end-of-life M&E systems, for example. And so it all gets wrapped up into that calculation. But by the time we got to stage 4, once you start to include building services, then the embodied carbon started to climb. However, at stage 4, it's still almost half of what the RIBA 2030 target is expecting now, let alone 12 months ago. The project also passed TM52, and for the sort of the office space building at the front, and it passed TM59 for the residential block at the back, and it will be within its sort of CIBSE comfort parameters for about 98% of the year. So, which is pretty. It is for a naturally the way it's heated and mechanically ventilated is a good outcome. We also looked at daylight and pretty much did a daylight factor calculation using climate-based daylight modelling, and that's where you use weather data for actual sunlight exposure as opposed to doing a ratio between lux levels on the working plane and lux levels on an overcast sky. So it's a little bit more of a complex calculation, but it's a little bit more realistic. And it also provides sort of early day indicators of incidents or potential overheating. So if we know, for example, in these corners where the daylight factor is very high, then we may have a room that's cause for concern. Because ideally, we're trying to get those daylight factors between 2 and 5. So we know that there's adequate daylight and it won't necessarily overheat. The third case study we did for Southampton City Council, and basically they were looking for really a template for developing about 10,000 homes. It's sort of, if you like, setting a sustainability design code. With, you know, and they when we first met, they weren't sure how to go about this. So we mooted the sustainable outcomes as a benchmark to aim for. And so we stuck with the preferred construction method. And with the design team, we had to look at or take into account acceptable step changes in construction products, practices and skills. But what we knew was we could get embodied carbon better than 2030, and the operational energy we could get better than 2025. And potable water, which this case study I'm going to focus on, we knew that we could get better than 2030 as well, but I'll demonstrate how we did that. And so these are the potable water targets. It's worth bearing in mind that we're living in the UK, we're ever increasingly a water stress country, and that basically means we don't have sufficient aquifer water capacity to meet our potable water demands. And so therefore we have to start to rethink what we include in terms of sanitary ware in our buildings and how we use it and what's important. And so what it did was look at a number of potential step changes. So we've got the current fixtures and fittings, flow rates there that would meet Part G. And so by sort of specifying those capacities, we know that we're coming at 110. I mean, the target is 125. And then by changing the flush rates or the flow rates of the taps and maybe the volume of the baths, then we can reduce that to below 2025 targets. The difficult change thereafter is really reducing the flow rates from taps even further, but begs the question as to whether we do away with baths in favour of just having, say, a wet room with showers only. And therefore, on that basis, we can get down to around about 70 litres per person per day, but it just requires that transition away from baths. And so with this transition and maybe the introduction of rainwater harvesting for use in toilets, for example, or washing machines, then we can reduce that to below 54 litres per person per day. So we know that this can be done. It's just that these aspirations have to be adopted. The last case study is residential projects in South London. It's an 8-unit residential project which was analysed at the end of 2020. The principles of construction are effectively business as usual, but it's got a very high-performing fabric-first solution with MVHR, air source heat pumps, along with some solar PV. And we've got Part G water usage down to 61 litres per person per day because there are no baths in these properties. And so what I've been doing this morning is actually updating the embodied carbon tool for the RIBA 2030 submission for the architect. And hopefully I'll be able to share my screen with that actually. And so these were the initial outcomes in 2020. So this was the operational energy, and it's broken down by property because form and orientation come into play. So house 1, for example, is it's only got a party wall on one wall, whereas house 2 to 6 are effectively a terrace, but adjoining to house 7, and then house 8 is the other end of terrace. So you benefit from only say losing heat loss through 5 surfaces rather than 6, and therefore those mid-terrace houses perform marginally better. And then with the solar PV, then obviously that has a benefit as well. The embodied carbon, this is where it gets interesting with the new targets, is that the project was 2025 compliant at stage 2. At stage 4, it's now around about the 500 kilograms mark. Now that, that the technical design has been fleshed out. But what's happened in that time is that the RIBA 2030 target has been elevated to 650. And so we now have a RIBA 2030 compliant project with business as usual principles of construction. So to wrap up, really, the successful design process really is to work to that digital plan of works. All the prompts are there, and designing really in context of the 3 pillars of sustainability. So, and keep it holistic from the start. So what we're trying to do is set aspirations with the end client at the end of the day. And then really at stage 1, you need to define those measurable goals and incorporate those into sustainable principles at stage 2. And then really it's a process of refinement and specification, and then it's delivery, and then assuring and learning from what's been delivered, so that we can feed back into the next set of aspirations that get set, but also ensure that the users going forward with their building operate it in the most sustainable manner, and they're comfortable, they're not overheating, and so you end up with a desirable outcome, really. And that whistle brings me to the end of my whistle-stop tour for questions.
Great, cheers, Richard. A lot to take in there. Fascinating
Yeah.
The changes on that last case study that you had there. Guys, feel free to post your questions, as I say, in the chat box. I'm particularly interested. I've got my own opinion, and Richard and I have been speaking a lot about this, about the changes to the embodied carbon values in the RIBA 2030 framework. In not a good way. I think it's becoming far too easy. It's not so much of a challenge, really. It's kind of a bit disappointing how relatively easy it is to get to that point. So do share your thoughts on that as well. So yeah, any questions you guys have got, do feel free to ping something in the chat box, and we'll try and answer any questions as best as we can do. Just whilst people are putting in questions there, I'll just remind you about next week's webinar. You've got me for 45 minutes. I'm going to be going over the eco project pitfalls again, and we are quickly coming up the week after that to the release of our new free embodied carbon calculator, which, as I say, is a new and improved version on some of the changes that Letty and RIBA have been making. So do sign up for those ones, and we'll be releasing that calculator as soon as it's available as well. Anybody got any questions? If not, I'll give you guys another kind of 30-60 seconds, and then we'll wrap it up. Right, so Stephen said there, yeah, the targets have changed, but the scope has too. And this is alludes to the embodied carbon, the RICS kind of scope for what you're including. It now includes building services and fixed fit out. Can I ask what numbers are used for building services when modelling embodied carbon?
We have different options for that. If the EPD is available and it's in the database, then we can include specific products. If not, then there are generic rates sort of per square metre that we can include for that. So for a sort of MVHR system, we can say, right, it's going to ventilate X metres squared of the internal floor area, and it will give us that relative calculation. Things like solar panels, we have specific EPDs for those, so we can be, it really depends on the product.
Yeah, I mean, you've obviously got TM65, which is the guidance on embodied carbon, and bits on refrigerant leakage and stuff, which obviously you're putting in a heat pump or a chiller, it's got refrigerant in it, that's included in the scope as well. So TM65 is really the kind of the source of data as well, as information in the software that we've got. Marta's asking, have you found any structural solutions that are better than others? Is this for, I'm assuming, Marta, you're asking about embodied carbon there, is that right?
Yeah, I mean, the most,
she's asking.
steel and concrete have the highest embodied carbon. However, we can address that, for example, by reusing steel or using high recycled content steel. Then that reduces it significantly. Concrete is still a bit of a controversial subject. I mean, you can use blast furnace slag, and that's the material that comes from coal. That's the waste material that comes from coal-fired power stations. So it sort of starts to replace the aggregate. Problem with that is, I mean, one of the arguments is that it's the offshoot of a fossil fuel energy, and therefore shouldn't really be classed as sort of carbon saving. And also, it's got practical considerations. It takes longer to cure. As it can't be used in all applications as well. There was some interesting news this week. It appeared on the BBC. Apparently there's a potential shortage of sand when it comes to concrete. And so they're looking at doing a percentage of sand replacement with repurposed plastic. So you grind down the plastic and it becomes, part of the bonding material. So that's going to be an interesting.
Marta has clarified her question, actually. She wasn't asking about embodied carbon, but actually the next step on from that, which is there a sweet spot when it comes to embodied carbon, but also thermal performance? So are there better products which kind of tick both of those boxes that you've come across, Richard?
The problem is, I mean, the more natural the material, if it's a grown material, whether it's off the back of a sheep or it's hemp, then it has, hemp is pretty much negative embodied global warming potential. Then the more natural the material, the less well performing it is as an insulation. So what that means is you have to have more of it. And so your wall thickness increases. So if you've got a timber frame building that's brick clad, maybe with a mix of PIR and mineral wool at the moment, then you could probably get away with a 200 mil thick timber frame, and then fill that with 100 mil of PIR and 50 mil mineral wool. Conversely, if you were then looking at wood fibre to fill those between the studs, then you might be looking at 250 to 300 mil. And so you end up then having to look very carefully at your structural engineering for your timber frame. CLT is particularly interesting because it has a thermal conductivity of its own. So therefore you can get some pretty good insulation of CLT. and then you can have your still have your cavity and fill that with say mineral wool or sheep's wool or hemp or wood fibre, and then clad it. And then really then it's a question of which cladding to choose, whether you're doing it for ease of replacement and maintenance, or are you doing it for durability?
Yeah.
So you
minefield.
could use,
Minefield. There's no one
can,
solution. There's no one silver bullet. That's what we're saying.
You could use virgin brick, and you've got a highly durable building. But equally, you could use recycled brick. But the challenge with recycled brick is obviously you've got to get your name down on the right quantity there and then in order to service your project.
So Chris has asked, thanks for that. Chris has asked, just going back to legislation, are we expecting any legislation to follow the challenge, the RIBA 2030 challenge, in order to force developers or clients to comply? Will the new Part L go far enough? Discuss.
Part L will do a lot for operational energy, because we're looking, I believe, was it 30% thereabouts improvement?
Yep.
So we're going to have to do that. And when you look at the London plan, they're looking for 10% improvement just using the fabric, and then another 20-30% improvement through the renewable energy systems. So there will be, it'd be nice to see a change in the carbon factor in Part L, so that we sort of level the playing field between gas and electricity, because then that suddenly makes heat pumps far more attractive in terms of the carbon emissions, and they use 3 to 5 times less energy to create the same amount of heat. So why wouldn't you leverage that market? I submitted some evidence to UK Parliament earlier in the year, and I made it quite clear on that I think there should be legislation surrounding overheating and embodied carbon in building regulations, because I think it's the only way we're going to leverage along with carbon taxation. But that's
I would, in brief, Chris, I don't think Part L is anywhere close to where these challenges are going to get to. You think the last regs were in 2013, they're going to update in 2021, not embodied carbon, sorry, operational energy, they're dropping by 31% by the end of the year, really, or the first kind of quarter of next year. The plan is for the Future Homes Standard. Again, by the middle of the decade, that will come down to maybe 70% CO2 emissions reduction. But there's no mention there of embodied carbon. There's a lot of lobbying. There was talk of a Part Z to the building regulations only very, very recently, and there's a lot of lobbying going on, and the Greater London Authority's already talking about, or they've gone out for consultation on whether embodied carbon should form part of regulation as well. So no, I don't think at the moment regulation is keeping up with the pressure from these frameworks. I mean, one hopes that it does, and it's certainly generating a lot of discussions which are going higher and higher up the tree. But no, I wouldn't rely on regulation in the short term solve any of the kind of the problems that the thinking between professionals is kind of coming up with, and that in many ways that's great to see, rather than everybody kind of resting on their laurels. But yeah, regulation is as probably expected is way behind what is actually happening and what people want to happen on the ground. Right, I think that's it. We're done on questions. Thanks very much, guys. Thanks for giving us your ears for an hour. Do sign up to the next webinar we've got for you, and look forward to seeing you next week. Take care. Bye-bye.
Bye.